this. Happy Thursday. Here we are. You're getting there. Did anyone not get the formula sheet last day? That's okay. You won't need it today. As I grabbed these, I was kind of also chatting with Allison. I remembered I had some homework. I was going to confirm the stretching. Is it by K or is it by a fraction of K? Anyways, I'll put that off. Oh gosh, I won't see you till on Tuesday. No classes on Tuesday. You have to wait a whole week? That's crazy. A whole week for more math. And I owe you 10 minutes today, if not more, because I keep going over time. I know that. I'm really good at blabbing. Oh, this is a delayed gratification versus a immediate gratification problem, I think. I like it at the end. All right. So last day, we introduced the concept of inverse functions, okay? And we'll see how far we get, but I was looking at chapter 2. We might just put it off until next week anyways, just for a nice clean break, but we'll see how the timing works out. What's an inverse function? The inverse function is a function. So if we have our inputs and our outputs, right? Our inputs and our outputs. Let's say we have 3 things, then we have 3 outputs, then our function has to be a special function. It has to be 1-to-1. Right? So then our f of x looks like this. It takes one input and it has to map to a singular output. Okay? So f of x must be 1-to-1 in order to have an inverse. Inverse. And that inverse takes the outputs, bless you, and maps back to the inputs. Okay. And we use the notation of f to the power of -1 of x. Now, instead of the power of -1, we call it just f inverse of x, is how you read it. Which means that the domain of the inverse is the old range of the original function, right? And the range of the inverse is the old domain of the original function, right? And so here we see that the domain of f inverse of x is the range of f of x, and the range of f inverse of x is the domain of f of x. Right, so they just swap. Yeah. There's a little tiny bit of confusion just because of the notation, right? But with a little bit of practice, you'll kind of get the hang of it. And so the inputs traditionally are the x's and the outputs are the f of x or the y's, right? But really the input of the inverse is the old y, but we still use x. And we'll see that come up again today. So we just want to always use X as a generic input, and it's not always the X. It can be the Y if we're putting it into the inverse. So, any questions before we get started? Try for Thursday. Well, here we are on Thursday. Delete that. Bump this up. So just like before, we can have functions given as tables, or we can have functions given as graphs, or most commonly we have functions given as mathematical functions. And so we'll work through those three different scenarios to solve these examples. So if we have f of x, here's a little itty bitty f of x. If you have to evaluate the inverse of f at 3, what does that mean? It means you go from the output of f of x where it's 3, and you move backwards to find the original input. So if you wanted to, you could visualize this function as 1, 2, 3, 4, with the outputs 3, 5, 7, 9. And the original function f of x goes like this, which means that the inverse goes the other way. Right? If the input is 3, the output is 1. The input is 5, the output is 2 for the inverse. 7 goes to 3 and 9 goes to 4 for the inverse. So you don't have to do this, but if you prefer it over the table, notice that it's just the same thing as the table, right? Just kind of more visual, I think, but they're the same. You can just smoosh them together and get the table. What if the inverse of x and we want to find where the output is 3? Now, the output of the inverse is 3, which means that the input must be 7 into the inverse. Right? So we're moving kind of backwards in a way. Questions about that one? I always think the easiest one is the graph version. Wait, is the graph example. So if we have f of x, the original function here, so line on the graph. With the graph, we can check to make sure it's a function, right? Using the vertical line test, looks like it's only going to pass once, so that's good. So it is a function. Then we move on to the horizontal line test to make sure it's 1-to-1, because we need it to be 1-to-1 in order to have an inverse. And when I do my horizontal lines, it looks like it'll only cross at one point ever, and so it is 1-to-1. Right? Which is why we had to learn those tricks in the first place. Now, if I want to take this graph of a function and evaluate the inverse at 3, what does that mean? It means I'm moving backwards, essentially. Right? So from 3, I want to move onto the curve and then down to find the original input. So I get 1. If I have the output of the inverse. Now, if you remember just how it goes, right? The output of the inverse is actually the input of the original function, right? And so if the output of the inverse is 4, I want to trace it back to the input that makes that happen. And so from here, from 4, I'm going up and over, so x must be 2 from the graph. Okay. Good. I have add 2 pages for work for each of these, so finally an example using mathematical function. So what we're building up to. Okay. There are steps to finding an inverse. And if you have found the inverse in the past, you might use slightly different steps. I'll introduce the ones that I use. But if you've done it in the past, then there are kind of a couple of different ways that you can do it, but you end up with the same result. Okay. So to find the inverse, to find the inverse of f of x, so any function, first you want to make sure that it's 1-to-1, right? It's a function and it's 1-to-1. Let's just confirm. I'll just confirm this one visually using Desmos. What was it? 3x minus 5. It's going to be a line. So I feel good about my Desmos has been acting up. Watch. Yeah. Just kind of like uses the line to create, I don't know what it does. Anyways, it's just a straight line. Right. So it's a function and it's 1-to-1. I feel good. Moving ahead. Okay. And so to find the inverse of any f of x, right? Step 1, ensure f of x is 1-to-1. Will I make you do it? Remember from last day, you can use function compositions, but I can't remember. Oh, that's why. Okay. Never mind. No, I don't make you do it. You're off the hook. I'll just tell you it's 1-to-1. Huh? In this case, we graphed it and it looked something like this. Probably like this. F of x equals 3x minus 5 is 1-to-1. And I should maybe use a different color here. Stop. How about light blue? Let me just clean this up. Okay, got a couple of steps to go. All right, so what we're doing when we find the inverse is we're essentially reversing the function, right? And so the outputs become the inputs right? So my x's become the y's. And so the first thing I want to do is replace f of x with y. Just makes it easier to look at. In this case, that means y equals 3x minus 5. Oh, that's an easy step. Can do that. Then what you're going to do is you're going to solve for x, right? Because the x is now going to be your new output, right? And so now, next step, solve for x. From y equals 3x minus 5, what do we get? I get y plus 5 equals 3x. I like to have my x on the left-hand side, and in the same move, I'll divide by 3. Oops, 3, not 5. So I get y plus 5 divided by 3. Here's where it gets a little bit boggy, because now your input is your y, right? And your output is your x. But remember, we still use x as a generic input and y as a generic output, even for the inverse. And so what you're going to do is you're going to rewrite x as y and y as x. And that's where, if you've solved for the inverse in the past, then potentially you swapped them up here, right? Replace your y with x and your x with y, and you would end up in the same place, but then you would solve for y, right? So, but I like this method. They're the same, but rewrite x as y and y as x. So then I get y is x plus 5 over 3. Remembering now that this is your inverse. Page. And now write the inverse as f inverse of x, which is why we had to have the x as the input, right? Because just generically, it is the input. So then I can replace my y with f inverse of x. Notice that my input here has to be the same variable as what's in my formula. And so I get f, oopsies, light blue. F inverse of x must be x plus 5 over 3. Okay. Finally, what I'll ask you to do, so that is the inverse. You found the inverse, right? X plus 5 over 3. I don't think it's terribly obvious that 3x minus 5, the inverse becomes something like x plus 5 over 3, right? But if you solve for y or x, I guess, then you've moved things over and you've kind of undone the function, right? And so that's how we move backwards. Now, I will always get you to find the inverse of a function. Then I'll get you to confirm that it is in fact the inverse. How do we do that? That's nice. These are kind of big questions, and it's always nice to check your work at the end, right? And be able to check your work and make sure that you did the right thing. So then confirm the inverse you found is indeed the inverse. The fact we'll rely on is that f composed with the inverse should be x. If I put the inverse into the original function, I should get back to the original input. And the inverse composed with the original function at x should also just give me x. So we're going to do these two function compositions, and I like to do them kind of side by side, otherwise it takes up a ton of space. So what I'll do is I'll just kind of shimmy this over here. And say, okay, well, our f of x, let's write it down, was 3x minus 5. And let me just confirm, 3x minus 5, okay, good. And our inverse was x plus 5 over 3. Just as a little reminder of what these two functions are. Okay. Which means that f composed with the inverse as its input, let's scoot this over. The inverse function becomes the input, right? So this is going to be f at x plus 5 over 3. Wherever I see an x, I'm going to replace it with x plus 5 over 3. So this becomes f at x plus 5 over 3. Now in the original function, right, wherever I see an x, I replace it with x plus 5 over 3, all as one thing, right? Careful about that. So then I get 3. I'll use big square brackets just to highlight that it's its own thing. Then minus 5. Ah, looks promising. 3 over 3, that's going to cancel. Then I'm left with x plus 5 minus 5. Ka-ching. So I'll start by canceling this 3 over 3. Oops, wrong color. Then I'm left with x plus 5 minus 5, which is x. That's always really satisfying, right? When you can get back to your x, even if the function composition is quite complicated, right? In the end, things will cancel out and you'll end up at x. And now I feel confident saying that, okay, I did find the right inverse, but to do it totally properly, we'll do this function composition as well, just to make sure, because they both have to be true. So if I start at f inverse of f of x, now f of x is my input into the inverse. And so we'll start here, f inverse at 3x minus 5. Wherever I see an x in the inverse now, I replace it with 3x minus 5. And so I get 3x minus 5, oops, minus 5, plus 5, then divided by 3. When I simplify this, right, 3x minus 5 plus 5, I get minus 5 plus 5, those will go away. And then I'm left with 3x over 3, which of course is the same as 1x. So again, I get back to x. So the question will say, confirm the inverse you found is indeed the inverse. Therefore, f inverse of x equals x plus 5 over 3 is indeed the inverse of f of x equals 3x minus 5. Therefore, f inverse of x, which was x plus 5 over 3, is indeed the inverse of, I'll squeeze it in here, f of x is 3x minus 5. Pretty fun. And a great way for me to test your function compositions as well. Wow, I know. Fancy that. All these things build on each other. Sometimes they don't. Okay. Any questions about that one?
Just checking one of those two methods is good enough, or should we be doing both?
I want you to do both because the simplification is just slightly different in both. And so I want to see both. So to recap, you rewrite your function with a y instead of your f of x. And then you rearrange and you can solve for x. Right? And so that's your new output. You rewrite x as y and y as x. Just kind of swap those. Okay. And then you can write the inverse as the inverse, f inverse of x. So usually I give you a function, right? And I say find the part A, find the inverse, right? And then you do that. Part B, confirm that the inverse is indeed the inverse. Okay. Sometimes we can have a function like x minus 3 squared. X minus 3 squared from last day, we know what it looks like. We have a pretty good idea of what it looks like. What will it look like? Should look something like, whoops, like this. I'll use orange maybe. 1, 2, 3. Where did I move 3? I take my parabola, which starts off, whoops, kind of like this. And x minus 3 manipulates the horizontal axis, right? So here's x squared. And so then I move this whole thing, let's see here, over 3 units to the right from last day. This parabola shifts over 3 units. So this is the graph of f of x equals x minus 3 squared. This is about as far as I expect you to be able to visualize the graph, right? Maybe an x squared, maybe it's moved up, maybe it's moved down, left to right, but that's it. Okay? You should be able to visualize those just like we did. So, first of all, we can use the vertical line test to confirm that it is a function, and it is, right? And so the vertical line test confirms f of x is a function. What's the problem though? Then I move on to the horizontal line test. And I cross the line, or I cross the graph twice in almost every spot except for 3, right? And so then that means it's not one-to-one, right? But what we do in that case is we just restrict the domain so that it is one-to-one. Right? So now if I draw horizontal lines, the HLT, the horizontal line test, shows f of x is not one-to-one. So to find the inverse, we need to restrict the domain. So to find the inverse, we restrict the domain. And we restrict it to something that is one-to-one. Now we've got a couple of options. So here, find the domain on which this function x minus 3 squared is one-to-one, and then find an inverse on that restricted domain. And so we're going to pick a domain first, and then we'll find the inverse. So it's I wouldn't say small, but it is an additional step that we need to do, restrict the domain. So we've got some options. So for our restricted domain, if I just make a copy of this thing, copy, paste. Oh, of course it pasted this thing too. Ah, the one thing I wanted. At least I had some clues. But now I wanna. That doesn't look very good, does it? Let me try again. Just freehand. There. We've got some options. There are kind of 3 main options that I want to talk about. So I'll just go ahead and make 3 copies right away. First one is the one I prefer. I prefer to go from 3, and I like positive numbers, right? And so here, 3 outwards. So then this section would be my restricted domain, which means I'm ignoring this arm, right? I do want to include 3, right? Because that's the lowest point of my parabola. And so then if I include 3, it just makes for a nice clean start. And so here, the domain using interval notation can be from 3 to infinity. That's a restricted domain. Now, if I only look at the highlighted section, right, then it is one-to-one, right? All those horizontal lines work, right? If you ignore the non-highlighted part. So then, of course, what's the other option? The other option would be the other arm. That's fine. And because we're doing these individually, there wouldn't be any overlap. So I would want to include the 3 as well. Okay. Which means that in this case, my restricted domain would start at -infinity and go up to and including 3. Notice that these two domains are the largest possible domains where I have a one-to-one function. Okay? And that's usually what we're striving for, kind of the largest possible domain. So here, for these two, notice these are the largest possible domains where the function is one-to-one, where the function is one-to-one. This is good, so I'll just write that's what you want in brackets here. So that's what you're going for. Either of those would work. Okay. Technically, if you were crazy, you could do something like, I don't know, 3 to 5. That's a restricted domain. And on this little path here, all right, 3 to 5, even including 3 and 5, it is one-to-one there, but it's not the largest possible domain. So technically, yes, this is a restricted domain where it is one-to-one, but I want you to use the biggest possible one. Okay? And so here, if the domain, a possible restricted domain, it's true, 3 to 5, for example, I'll say, while this restricted domain is one-to-one, we usually try to go for the largest possible domain we can. Okay. Or I'll say we want to use the largest possible domain as the 2 examples above. Technically true, yes, but you want to use the biggest one. In our example, I'll use the first one. And then you'll see what would change, and I'll point out what would change if we were to use the second one. And so the next part that we want to do, okay, find a domain on which this function is one-to-one. We did that. We've got 2 options. We'll pick one and find an inverse on that restricted domain. So now we're going to find the inverse. So now, find the inverse on the restricted domain I'll say I will use 3 to infinity, but I'll point out where it would be different if you wanted to use -infinity to 3. Okay. We've got our function. F of x is x minus 3 squared. We've already determined the domain where it's 1 to 1, and so I'll kind of skip that step and jump straight to the step where I rewrite f of x as y. That's kind of a breezy step. X minus 3 squared is y. Then I want to solve for x. So my next step, solve for x. Rearranging here. When I take the square root, what happens? I need to account for the positive and the negative version, right, of the square root. And so I get this, or I'll start here. I'll write it because it's on a new page there. When I take the square root of y, I get a positive and a negative version of this thing. Equals x minus 3. Okay. But only one of those positives or negatives will apply depending on the domain I chose. Okay. And so here, recall the domain is from 3 to infinity. Okay. So 3 from infinity, if I have x equals 3, right? 3 minus 3 is 0. Okay, so that's positive. Right? What if I move up one? 4, right? Moving my way to infinity nice and slowly here, right? 4 minus 3 is 1, positive. Okay, so I've got kind of 2 positive options. 5 minus 3, positive again, right? As I move further and further towards infinity, it's just going to be positive, right? And so the domain will only yield positive values. Okay. Which means we only keep the positive. This is where it would be different, right? If you had restricted your domain from negative infinity to 3, right? Then 2 minus 3 is negative. 1 minus 3 is negative. 3 minus 3 is 0. So then it would go all the way up to from negative infinity to 0, right? And so then in that case, you would use the negatives, right? And ditch the positives. So, therefore, on the restricted domain, I just have the root of y. And if you want, you can have a plus out front there just to remind yourself, but you don't have to. Must be x minus 3. I'm still solving for x, but it's a little bit cleaner now than the plus minus. And so then I have x must be the root of y plus 3, or 3 plus root y if you prefer. If you don't want to have that root hanging out. Good. So then we've solved for x. Now we need to rewrite our x as our y and our y as our x, right? Just to conform to that typical notation that we use. And so rewrite x as y and y as x. So then I get y is the root of x plus 3. And notice that I'm putting that hook on the root just to show that that 3 is not inside the root, right? If you're not very good at remembering that hook, right? And maybe you're sloppy about your root and it looks like the 3 is underneath, then I would encourage you to rewrite it as 3 plus root x instead, right? So the root is at the end, right? And so here, or 3 plus root x. They're the same, right? A plus b is the same as b plus a. And it just makes it a little bit cleaner to look at if you prefer. Finally, we have the inverse, right? So we can write it as the inverse. Right, as the inverse, as f inverse of x. I get f inverse of x is the root of x plus 3. Uh-oh. What's our next step? Usually I give it to you as a part in the question, but we're going to confirm, right? Confirm that this is the inverse. Confirm we have found the inverse. We do the same thing, our function compositions, right? F composed with the inverse has to be x, and the inverse composed with f has to be x. And so I like to set them up as well, first I like to remind myself what my functions are. F of x was x minus 3 squared. And the inverse of f of x is the root of x plus 3. Now I can do the function compositions. Okay, so f of the inverse, start there. You don't have to do them side by side. I just like to do them side by side so you're not using up a ton of space. And so I can keep it on the same page. Okay, using my inverse function as the input into my original function, it's going to look like this. I have f of the root of x plus 3. Notice that I don't try to jump right into stuffing it in, right? I like to have kind of a stopping point where I replace the inverse with what the inverse actually is. And then I go to the next step. Because now, as long as I treat root x plus 3 as one thing, right, then I get root x plus 3 is one thing, then minus 3, and then squared. If I simplify this, plus 3 minus 3, that'll go to 0. Bing, bing. Then I'm left with the root of x squared, but the root of x squared is just x. Phew. You can see how satisfying that is. So then you can relax. I feel good about the inverse I found, but let's do the other one, the other function composition, just in case. Has to be true for both. The inverse at x minus 3 squared. Wherever I see an x in the inverse, I'm going to replace it with x minus 3 squared. I get the root of x minus 3 squared, then plus 3. X minus 3 squared square rooted is great because it becomes x minus 3, then plus 3, which goes away, and I'm left with x. So besides this additional layer of figuring out, okay, well, which one of these roots, is it the positive root or the negative root, matches the domain that I chose, right? Where I've decided it's 1-to-1, right? Other than that, it's the same procedure, right? Nice. Therefore, f inverse of x equal to the root of x plus 3 is indeed the inverse of f of x, which is x minus 3 squared. I will clarify on the restricted domain. On the restricted domain, because we did add that 3 to infinity. Oops. Nice. Looks like we will start chapter 2. Can't quite do it this early. Any questions though before we start the next chapter? This marks the end of chapter 1. Kind of a long chapter, I think. Lots of kind of topics that we introduce, right? And some of them feel a lot more complicated than what we're going to go back to. Like I warned you last day, right? We now are going to just go back to lines. But any questions before we do?
Why is functions equal?
Almost everything we do, especially now that we've introduced a restricted domain, right? We can restrict a domain until we have a function, right? And so almost everything we do in math involves functions. I know. Inputs, outputs. Dang. So now, it does feel weird, but in chapter 2, we go back to linear functions. What does linear mean? It means it's just a straight line, right? And so here, linear means a straight line. And you might remember something like y equals mx plus b. Right? The slope of the line is m and the y-intercept of the line is b. But before we do that, we've got this example. Suppose you're running a coffee stand. Doesn't that sound so nice instead of being in school? Just go to work, and then when you're done, you shut it down, and you can go home, do whatever you want. That sounds nice, right? I know. But then when you're out of school, you're going to start romanticizing being in school. Oh, it was so nice. All I had to do was just study for my classes, hang out with my friends. So you really can't win. I'll tell you right now. But suppose you're running a coffee stand. The labor cost is $90 a day. You still have to pay whoever's working there $90. And the per cup cost is $130. So we've got these costs, and of course, ideally, we make some revenue, but we're not talking about that aspect right now. So our cost, the cost must be our labor. I'll spell it with a U because I find that kind of painful. Plus the per cup cost times the number of cups, right? Usually you sell more than one cup, right? But each cup has a cost. And so the per cup cost times the number of cups. If we let the number of cups be X, because I want to use this function and I want to input, okay, I sold this many cups, my costs would be what? Right? And so the number of cups is the input, which means that the cost, we could use C of X for the cost of X cups, which is the output, which is the cost of X cups. And labor. Just to clarify, it's the total cost. So then my labor is 90. My per cup cost is $1.30 times X, which represents the number of cups. So then I can put in any value of X. I sold 120 cups. What's my cost? Then of course, if I sell each cup for $4, then I would be making some revenue. But like I said, we're just writing an equation for the cost. This, notice, is the same format, and I guess I should include the C of X. This is the same format as y equals b plus m times x. Mx plus b is the same as b plus mx, but typically what happens is when we talk about a line, right, our initial cost is $90. You have to pay that even if you sell 0 cups, right? So that's a cost no matter what. So then that's your y-intercept, and then we increase it by 1.3, or the slope, times however many cups we've sold. And so, or y equals mx plus b, which would look like what? C of x is 1.30x plus 90. That's the same, right? So the order that you write these in doesn't really matter, right? What are you looking out for as we're dealing with lines? You're looking for just one x, right? No x squareds, no x to the 3s, right? Just the highest power of x is 1. Notice the highest power of x is 1, right? That's what makes it a line. Therefore, it is a line. In the next chapter, we look at quadratics, where the highest power of x is 2, right? Look at the behavior of that, and then we can build out from there. Now, what color haven't I used? I'll revert back to dark blue, where B, just as a reminder, represents the y-intercept. This, and do I do it? Sorry, let me just scroll ahead. Okay, I'll have an opportunity to do it later, so I'll just hold off. So where b is the y-intercept, and of course m is the slope. So whatever is attached to the x is the slope. Everything I just wrote is kind of summarized in this box, but they tend to be kind of boggy. So a linear function is a function whose graph produces a line, which means that we can always write them in this form, like I said, b plus mx or mx plus b, but usually I think in high school we use y equals mx plus b as our kind of go-to line. B is the initial starting value of the function when the input x is 0. And m is the constant rate of change of the function, which is the slope. So here, many people like to write the linear function in the form b plus mx because it corresponds to the way we speak. The output starts at b and increases at a rate of m. Right? You don't have to. They're equivalent. So I did keep it just because a lot of the examples have b plus mx, right? Just because that's the form that we tend to read it in. The slope can be increasing or decreasing. Now we've already worked with the rate of change, right? The average rate of change, and we've talked about increasing functions and decreasing functions. And we even talked about nonlinear functions, right? Parabolas, curves, talking about if they're increasing or decreasing. So we've gone beyond this already, right? But if I have a straight line, then I have kind of three options for if it's increasing or decreasing, or maybe it's doing neither, right? And so what those slopes are going to look like. So if the slope is positive, then we say it's an increasing function, right? Or it's just a positive line. Looks something like this. M is greater than 0. It makes a positive or increasing slope or line. It's increasing if as x is increasing, y is increasing, but I like to, on the right-hand side, I like to kind of imagine a little arrow, and the arrow's going up, right? And so then that reminds me that it's increasing. Versus my next option, which would look something like this. Here, my slope is going to be less than 0, which means we have a negative slope or a decreasing function. And again, as long as you put your little imaginary arrow on the right-hand side, right, notice that it's going down, right? So it's decreasing. Our final option is the special case where we have this, oh, I need to make it thicker. Just a horizontal line. Okay. I guess technically we have a fourth option, but we'll leave that. Here we have a slope of 0. Right? If you try to do rise over run with 0 rise, right? 0 divided by anything is 0, right? And so if the slope is 0, the rate of change is 0, right? Then this just becomes a horizontal line which passes through at 0b. But that's a special case where the slope is 0. And at the slope of 0, right, it's neither increasing nor decreasing, it's not doing anything. Okay. In terms of visualizing our lines, right, knowing if the slope is positive, that it's going to be going up, 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 and knowing if it's negative, that it should be going down, 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 right, that'll help us kind of visualize the problem. Huh? Okay. How about an example? The value of a car depreciates over time, and in this case, according to this equation, V of t is 13,000 minus 2,000 times t. And there's a couple of things that we'll have to assume, such as t is likely in years, right? So let's assume t is time in years. Be really disappointing if it was in months or something like that. What would that mean? Well, if we had to interpret this thing, v must mean the value, right? And so the value after t years, right, is going to be 13,000. And then for each year, each additional year, we subtract $2,000 from the value. Okay. And so we have v of t, let me just write it out here. 13,000 minus 2,000 times t. So here, the value after t years. This 13,000 must be the initial value of the car, right? When t is 0, right? My value of the car, well, must be 13,000. Okay. And so this must be the initial value of the car at t equals 0. Right? After 0 years, 13,000. For each additional year, t, right, I subtract $2,000. So for each year, t, we subtract $2,000 from the value, from the initial value, I should say. This is where I wanted to add something, I think. So that's how we would interpret this equation, right? We have some input t and an output of the value. Okay. From here, you can solve things like, when is it not worth anything, right? And so what do we know about this line, 13,000 minus 2,000 t, right? If t is my input, that's essentially my x, right? And so I have a negative slope, so I know the value of the car is just plummeting. We know that about cars, right? And so if I wanted to, I could restart Desmos, hoping it works this time. That's a good place to start. And then I could graph $13,000 minus 2,000 X. Doesn't look very good. It is a line. It's going down like this, but that didn't help, did it? I'll do this. This line should, let's use this, should start at 13,000 and then have a slope of negative 2,000, right? Where T is in the place of my X, and the value at time point T, right, is 13,000. How long until the value is $0? Right, we can solve that. How many years until the value of the car is $0? Okay. I have my value function, right? And I want to solve for the t that makes this value 0. Right? We can do that. V of t is 13,000 minus 2,000 t, forcing the value to be 0 and solving for t. I get negative 13,000 is negative 2,000 t. I don't know, 13,000 divided by 2,000. Is it 6? I heard but now I've already started, so I can't stop. 6.5 years. So you can use linear functions like that. What does that tell us? Well, that this point here where it crosses, it goes down into a negative value, must be 6.5. Oh. Now, I need you to know the general interpretation of the intercept and the slope. And so here, I'll just indicate that this is the end of this example here, because just want to squeeze something in. The general interpretations of B and M in y equals mx plus b. We'll start with B. B is the y-intercept. And if we think about y equals mx plus b, well, and we were already given the clue that, okay, that's the value of y when x is 0, and that is part of our interpretation. Okay? And so the intercept is the value of y when x is 0. Okay? Or I'll incorporate b is the value of y when x is 0. So I want you to remember that kind of general interpretation. So I'll highlight this guy here. And the general interpretation of m, which is your slope, is, okay, your slope is attached to your x, so it will have something to do with your x, right? In fact, it's for each unit increase in x, right? So for each additional year, for example, right? Then I'm going to see a slope increase, and we use the word increase just generically, right? In y. Okay. And so we get for each unit increase in x, we will see a slope, which is your m, unit increase, oops, in y. Now, I always use the increase, right? So for example, right, in our value function that we had, how would we interpret this slope? We would say for each unit increase in the number of years, right, then we're going to see a negative 2,000 unit increase in the value of the car, right? And so a negative increase makes a decrease, right? And so I don't bother with the decrease increase because you want to be careful, because if you use the term decrease here, right, and you told me that it's a negative decrease, well, a negative decrease is actually an increase, right? So I always just use the increase and keep the slope negative here, right? And, but I will make a note, right, because depending on kind of how comfortable you are allowed to say it's a decrease, but then it would be a 2,000 unit decrease, right? You'd have to drop the negative. So here, notice a negative 2,000 unit increase is a 2,000 unit decrease. Right. So if you want to, you can make that swap, but I don't really bother. All right, just keep the slope as is and call it an increase always. Nice. Interesting. All right. Worry, I've gone too fast. Didn't expect to. Oh well. We've already calculated some rates of change. And in our case, for linear functions, it's going to be the slope of a linear function, right? We've calculated average rates of change already, and so we've seen these formulas. But now we see them again, and we're going to use them to find the slope. So if I have 2 points, x1, y1, and x2, y2, right? Then if we're going to find the slope of this thing, then we need the change in output over the change in input. That's our rise over run, right? Delta y means the change in y, and delta x means the change in x, right? And just like before, we've seen this little guy before. just bring this m over here. So our slope is going to be y2 minus y1 over x2 minus x1. If we have a linear function, right, so if it's a straight line, then of course this is the slope of the line. Right? So we've already done this. We even extended to the function notation, right? F of x2 minus f of x1, taking the place of y2 minus y1, just a slightly fancier way, but they all do the same thing. So let's practice again. Even though we've already done it earlier. I can't remember which section, 1.2, 1.3? Okay. We want to find the rate of change between -2,3 and 4,0. Find the slope. Okay. y2 minus y1 over x2 minus x1. Doesn't matter which point you use as your first point and your second point, right? Depending on how flexy you are, right? It tends to be more convenient to use the first point as point 2 and your second point as point 1, just because that's how they appear in your formula. But I'll use them in the order that they appear. But you'll find the same thing. All right. And so here I'll call this x1, y1. And this I'll call x2, y2. So then I get 0 minus 3 divided by 4 minus -2. Oh, I changed colors all of a sudden. Let me change it back. There. I get -3 over 4 minus -2. 4 minus -2 is 4 plus 2, putting me at 6. I'm fine with not simplifying this, right? Your calculator, which is part of the reason you have these fancy calculators, if you do put in -3 divided by 6, and then hit equals, it should just simplify it for you, -1/2. Right? And so they're the same in terms of a decimal, right? But your fancy calculators will just simplify it for you, which is the reason why I don't really care either way. Right? So if you jump to the simplified version, fine, but I'm just going to keep it here. We can simplify, but I will not require it. Right. Sometimes it makes it easier, and then I will, but generally I don't. What if we're given f of 2 is 3 and f of 4 is 7? Yeah. So now, right, I have my function notation, but I still remember I can find my slope, and I'll copy this, bring it down here. As long as I, again, use one of these functions as my first and the other one as my second, it doesn't matter, right? And so if this is my first function, x1 is 2, y1 is 3, right? So if you wanted to, you could translate this into 2, 3, and 4, 7, if you wanted to. If you prefer working with points instead of the function notation, that's fine. I'm just going to skip to the function notation version. F of x2 minus f of x1 over x2 minus x1. If I use this as my function 1, and this as my function 2, f of x2 is 7. F of x1 is 3 over x2, which is 4, minus x1, which is 2. Four over 2. Okay, I will simplify that. But I'll keep it over here. Slope of 2. Because I have a page break. I don't like to do that, but when it generates the PDF, it makes a mess if it's on the other page. Okay, so we know how to find some slopes. Guess I can delete this page here. If we're told that the number of students grew from 4,000 in 2008 to a whopping 43,000 in 2010, so just in 2 years, that's crazy. Can you imagine? If we assume the number of students is growing linearly, right, then find the rate of change, right, which is really asking you to find the slope. Right? So here, find m. What do we need to find the slope? Well, we need 2 points, right? We are given 2 points, but we have to think a little bit about inputs and outputs, right? And so our input, right, there's one more reasonable option than the other one. Yeah. And so we are talking about the number of students and the year. Right? I think it will be cleaner to use the year as my input, and then it tells me how many students there were. Right? And so first thing I'm going to do is let the year be the input, which means that X is the year. Huh? You could go the other way, but it's just harder to make sense of, in my opinion. If you say, well, if I had 4,000 students, then the year must have been 2008. It does work, right? But I think it's a little bit harder and less intuitive. And so then the number of students is the output. So means Y is the number of students. Okay. Now I am given 2 points, right? Once we've decided what our X is and what our Y is, right? We are given 2 points. Oh, okay, I'll need to move this down, I think. I know. So we're given 2 points. X is the input, so in the year 2008, the output was 4,000 students. And our second point, when the year was 2010, the output is 43,000. I wonder if there's an extra zero there. Just seems like a huge leap. Just thinking about your slope. You expect it to be quite large, right? Because if you're visualizing this relationship, so from 2000 we were at 4,000, and then all of a sudden 2010, 2 years later, you're at 43,000. Making me think it's a typo, but that's okay, right? So I'm expecting this slope to be super, super steep, right? So quite large. So now that we've boiled it down to 2 points, right? Then I can find the slope. M is y2 minus y1. Notice that I'm choosing the function that I'll use, the version of M using the y's or the f of x's, right? Depending on what I am given, right? And so kind of be flexy there. But I get M is 43,000 minus 4,000. Uh-oh, math. Divided by 2010 minus 2008. That's math I can do, but together, not quite. Okay. 39,000 divided by 2. I do get this quite large slope of 19,500. How can we interpret this? For each additional year, right, we expect the number of students to increase by 19,500. Therefore, for each additional year, usually we say we expect, but that's more for statistics than here. So the number of students, here it's solidified. The number of students will increase by 19,500. You can try it, right? Starting at 4,000 plus 19,500 puts me at 23,500 plus another 19,500. I get to 43,000. Oh. Nice. Let me. You know what? We're gonna save writing linear equations for when you're fresh next week. Let you work on your slopes. How about that? Huh? I need you fresh for this. If you have any questions, let me know. Otherwise, I hope you enjoy your kind of long weekend. Long weekend from me, at least. All right, I'll end this.